I'm already really enjoying the program. So I'm going to talk about decomposition theories and minimizing Hausdorff dimension of Julia sets in the context of Sullivan's dictionary. So this is the question I'm recently working on. So this is quadratic rational maps, sequence of quadratic rational maps in the hyperbolic components containing the Basilica polynomial. So it can be explicitly written by this formula. And when you approach t to -1, then the limit is a degenerate quadratic rational map. So if you imagine the moduli space of quadratic rational maps, then this sequence goes to infinity, the moduli space. So you can see that the Julia set converges to around the circle. It's not hard to show they actually converges in the Hausdorff topology, but it doesn't mean that the Hausdorff dimension converges to 1 as well. And I'm really interested in showing this convergence of Hausdorff dimension. And there's some beautiful background and motivating stories about these questions. That's my topic of this talk. So let's begin with some some easy or well-known decomposition theory for manifold. So if you're given a surface, then we cut the surface along the simple closed curve, then you can express it as the connect sum of two tori. So generally, surface of genus G can be decomposed along G-1 simple closed curve, then this connect sum of the G many tori. So this is what we learned in some topology class. And in one-dimensional higher, and it's a three manifold, we do similar thing. So we first try to cut three manifold along spheres because the circle is one-dimensional manifold, and so we try to cut the three manifold along the simplest two manifold first. So cut them along the essential spheres. Then actually we can get m's connect sum of some AIs, and this finite many components, and this decomposition unique, which is called the prime decomposition. And each AI does not contain a essential sphere, which is called aspherical. But it's not very satisfying because there are so many aspherical three manifold. There are so many difficult three manifold still. So what we can do next, so we want to further decompose aspherical manifold. So fortunately, we have more surfaces than sphere. So next, we can try to cut aspherical three manifold along tori. The reasonable next step. It is called JSJ decomposition. Named after Jaco, Shallon, and Johansen. And also should remark that Thurston's one of many celebrated theorem tells that each piece of JSJ decomposition has 1 out of 8 geometries. So Thurston's theorem can be seen in this context. And more interestingly, hyperbolic geometry is one of these 8 geometry. And if the manifold is A toroidal, then it has some hyperbolic geometry. And then, for hyperbolic atoroidal is equivalent to hyperbolic three-manifold. So this equivalence is called the hyperbolization theorem as well. It's a part of Thurston's geometrization program. So for atoroidal three-manifold, we can also further decompose it along some disks and annuli. So it is a part of JSJ decomposition. So this is a quick review of some decomposition theory in surface and three-manifold. So let's talk about some decomposition theory in the dynamics on the sphere. So we are interested in the post-critically finite rational maps or post-critically finite topological branches self-covering of the sphere. And let gamma be an F-invariant multicurve of this punctured sphere. So here I drew some green simple closed curve that consists that the union is F-invariant multicurve. If you pinch the sphere along those blue curves and you detach these small spheres, then this dynamics on the big sphere induce the dynamics among the small spheres, and you still have some marked points on the small spheres. Some of them are periodic and some of them are pre-periodic. And the first return map on the dynamics among small spheres is called small rational map, and we call them this decomposition of the rational map, post-critical finite rational map along the multicurve. And here we should remark that this is a topological surgery. So the outcome of this decomposition is some topological branches self-covering. And we use Thurston's characterization to realize this topological self-map to the rational map. So here is some funny examples, of decomposition. So it's a process tuning, called tuning. So we can make for two components the rabbit polynomial to rabbit polynomial as well. Then you have this more complicated rabbit picture. So in this case, you have 9 post-critical points. You can find the 3 cycles of simple closed curves. And if you decompose the sphere along the 3 cycles of simple closed curve, then you get 1 big sphere and 3 small spheres. And the dynamics of first return maps are all conjugate to the rabbit polynomial. And if you think about the airplane tuned with rabbit, then we have similar 3 cycles of simple closed curve. And if you decompose similarly, then you can pick the 3 rabbits out from the airplane. So this is some basic idea of the decomposition theory of post-critically finite rational maps. Here is a masterpiece drawn by Hubbard in 1980s. So it indicates the mating of basilica and rabbit polynomials. And here's more fancy animation of this mating polynomials. So for this rational map, you can find the equator, which is invariant, is fixed by the dynamics. And if you decompose the sphere along this equator, then you can decompose these quadrilateral maps into 2 polynomials, one basilica and one rabbit. So with this decomposition method, so Duco and Louis-Shankar later proved the following decomposition theory. So for any PCF rational map whose Spatu set is non-empty, then it can be decomposed by some multi-curve into Sierpinski carpet map and crochet maps. So Sierpinski carpet is the fractal obtained by removing the middle 1-9 square. And Sierpinski carpet map is a rational map whose Julia set is homeomorphic to the Sierpinski carpet. And the crochet map is a new family. So it's another elementary building block of their decomposition theory. So what is crochet map? So here is the 3 equivalent conditions describe crochet maps. First, any pair of two components can be joined by a chain of touching two components. So for example, if you pick 2 red two components, then you can find a finite length chain of touching two components connecting them. And if you pick 1 white and 1 red two components, then you should pass through some countably infinite chain of touching two components to get to this white component from red component. But you can still find this sequence of touching two components, joining them. Another criterion is if the set of local cut points totally disconnect the Julia set. So these touching points are the local cut points, and if you remove them, then the complements, every connected component of the complement is a singleton. And more important property is the following. So there exists some F invariant graph containing all the post-critical points such that the induced dynamics on this graph has topological entropy 0. And we call, if the map satisfies one of these properties, then we call it a crochet map. Is there any question? So here's a non-example. So if it's the carpet, then there's no pair of touching components, so it's obviously not crochet map. And for the rabbit-tuned carpet, if you pick 2 black two components with the same rabbit, then you can find a touching sequence of two components. But if you pick 1 two components of the one rabbit, and if you take the two component from different rabbit, then you cannot find the touching sequence of the components connecting them. And these are and this crochet map contains many infinite family of interesting rational maps. So polynomials are all crochet map, and mating of rabbit and basilica is a crochet map. And if every critical point is fixed points, then it's also a crochet map. And every PCF Newton maps is also crochet map. So here is some review on the decomposition theory and the crochet maps. So let's talk about some geometric side related to these maps. So a homeomorphism between 2 metric space is called quasi-symmetry if it satisfies this condition for some distortion function eta, but more intuitively, which is slightly weaker than the original quasi-symmetry, but these are equivalent in our case for the fractals on the sphere. So it tells that any ball image is a quasi-ball in a sense that the ratio of in radius and outer radius is uniformly bounded by some constant h. So in other words, it preserves the roundedness of the ball. And here's one of my favorite joke made by Duari. So this is the rabbit hyperbolic components in the Mandelbrot set. And if you move your primary points around within these rabbit hyperbolic components, then by the lambda lemma, your Julia set changes quasi-symmetrically. So if you make a movie of how Julia set changes, then you can see the belly dancing rabbit. So they belong to the same quasi-symmetric class. So Pan Su introduced a notion of conformal dimension, which is defined as the infimum Hausdorff dimension in the quasi-symmetric equivalent class of metric space. Then why should we care about conformal dimension? Because the reasonable deformation space are contained in the quasi-symmetric class in the complex dynamic side. But for geometric group theory, for Gromov hyperbolic space, the boundary has a canonical metric called visual metric. But the problem is it's not unique, but it's unique only up to quasi-symmetry. So if you want to get some geometrically meaningful invariant from visual metric, then you should take some infimum or supremum over the quasi-symmetric class. And supremum is always infinity. So infimum is kind of some canonical choice to get some geometric invariant. So this is my main work in my thesis. So for any post-critically finite hyperbolic rational map, F is the Croce map if and only if the conformal dimension of its Julia set is equal to 1. And being a Croce map is being a minimal building block in the Duke and Lucian isolators decomposition theory. And since for any hyperbolic rational map, the conformal dimension of its Julia set is at least 1, the right-hand side also the geometrically minimality. So they are equivalent. There's one of my ongoing project with Caroline. So we try to classify all the degree 2 hyperbolic Croce maps. And it's conjecture, but it's soon to be a theorem. Maybe we should make it a theorem during the program. So we expect that for quadratic case, every Croce map is either mating with core entropy 0 polynomial or capturing of core entropy 0 polynomial. These two are kind of expected classes, but there's one more interesting family. This can be obtained from type B capturing and certain parabolic implosion from there to make it type D hyperbolic rational map and plus satellite tuning. So, okay, is there any questions so far? So Sullivan dictionary is about analogies between two dynamical systems. One is complex dynamics of endomorphism of the Riemann sphere. And the other side is a group action. It's a discrete subgroup of PSL to C. And here, the limit set of this group is also fractal. It's analogies with the Julia sets in the complex dynamic side. So in a similar time, Carrasco and McKay proved the following theorem for Gromov hyperbolic groups. But if you translate their theorem to the manifold, then you can say that for hyperbolic 3 manifold with convex core, the conformal dimension of its limit set is equal to 1 if and only if the manifold can be decomposed by disks and annuli into some interval bundle over surfaces. And yeah, you see Duclos-Schleicher's theory, then Prosham map also can be decomposed into some more elementary building blocks. So these theorems are analogous in this context. And more interestingly, about 10 years ago, Kenner and Minsky-Taylor proved the following theorem. For a hyperbolic three-manifold within compressed boundary, if you take the infimum of the Hausdorff dimension over the deformation space of hyperbolic structure rather than the all quasi-symmetric equivalence class, then the infimum is equal to 1 if and only if the manifold is a generalized book of I bundle. So this deformation space of hyperbolic structure is a finite dimensional. So this is much smaller than the whole quasi-symmetric equivalence class of metric space. So infimum over smaller class gives you some possibly larger quantity. So what is a generalized book of I bundle? So this is a book of I bundle. So you first prepare some surfaces with boundary, and you also prepare one circle, which is called a binder. And the surfaces with boundaries are called pages. So you glue the boundary circles or pages with a single binder. And then you get some two-dimensional complex, and if you thicken them to a three-manifold, then it is called the book of I bundle. So you can think of it as some pages bounded by some binder. And the generalized book of I bundle is the pages are bounded by several different binders like this. So this is equivalent condition for the infimum Hausdorff dimension for the deformation space of hyperbolic structure is equal to 1. So the natural question is to translate this theorem to some complex dynamic side. So according to Sullivan dictionary, this deformation space of hyperbolic structure corresponds to hyperbolic components. Hyperbolic component can be understood as a deforming our dynamical system quasi-symmetrically. So these are questions asked by two people I respect. So in this context, Macmillan asked to classify hyperbolic components whose infimum Hausdorff dimension of Julia set is equal to 1. And maybe the basilica is the reasonable first example of this property. And Bisha asked the following question. Because the conformal dimension of the Julia set of basilica polynomial is equal to 1, so you should be able to find some sequence of metric which is quasi-symmetric to the Euclidean metric such that the Hausdorff dimension of the basilica Julia set with respect to this sequence of metric is decreasing to 1. So because the proof of this equality is implicit, so we don't understand what metric decrease the Hausdorff dimension to the infimum. And answering to these two questions converges to this specific example. So if this Julia set, the Hausdorff dimension of this Julia set converges to 1, then this answers the two questions. And I was stuck on this question over the last 3 years, and fortunately, Yusheng and I could make a progress on this question, and we showed that actually the Julia set, the Hausdorff dimension of this Julia set converges to 1. So basically we generalize this theorem by Macmillan, the convergence of the Hausdorff dimension. So he showed that when Fn is a sequence of geometrically finite rational map and its limit is also geometrically finite, and if the convergence is good, then the Julia set converges in Hausdorff topology, and also Hausdorff dimension also converges. And our case is similar, but the limit is the geometrically finite but degenerate rational map. So we employ some Macmillan's approach and we find some steps for the case when the limit is degenerate rational map. Okay, that's all.
Yes.
That's also a very important question. And what I also showed is when conformal dimension 1 is obtained, then it has to be Chebyshev polynomial. That is the only case, or the round circle. Yeah. So attainments give some strong rigidity even for the groups, Kleinian group side as well. Yeah.